Okay. Hello, everyone. Today it's a pleasure to have a local, our own Barbora Bezdekova from Haifa, who will speak on light propagation around compact relativistic sources in dispersive media. So Barbora has just joined us in the University of Haifa this year. Please, Barbora, take it away.
But I suppose she is now in Prague, no?
Actually not. I am at home, which is not Prague, so it's a small town in Moravia right now at the moment. But
I see. It's a small town in Moravia?
yes, near
Okay.
Brno. Brno is the second largest city.
Near Brno. Okay. Thank you.
So thank you for giving me opportunity to talk today. I would like to introduce my work, which I did mostly during my PhD in cooperation with Professor Jiří Bičák, but also with others, and I will briefly mention them. And the main topic of all this is basically doing or studying light trajectories in the case when around compact sources, in the case when this compact source is actually not surrounded by vacuum, which is usually done, but it's surrounded by some medium, which I will describe later. Typically, of course, such medium in astrophysical application would be plasma, but considering all plasma in all details as realistic as possible is quite a challenging task, and we are actually developing that in terms of analytical approach, but I would like to at least share some of the results based on the what we best things which we can do at the moment right now. So at first I will briefly put some motivation why it's useful to do such kind of studies analytically in the times when we have not only simulations but also observations. I will describe the formalism which I use for this, and because usually, or at least for me, most intuitive way how to study the properties of such systems in terms of deflection angle, I will describe also this approach, or at least understanding in this context, and then I will move to some examples what I got, and also conclude main findings which I obtained during my basically PhD. When you look on these pictures, which I am sure you know very well, you can see that for these observations, which were obtained 5 years ago by EHT, then also simulated or simulations came into the play in order to reproduce the picture, which is actually given here. When you can see that for different physical situations and settings and parameters of not only black hole but also the accretion disk, they basically were able to reproduce the original picture, at least very much similar to what they observed. So from these simulations, you are basically not able to distinguish which setting corresponds to the physical reality, because the output is more or less always the same and corresponds to the measured things very well. Other example would be for these simulations which were obtained for the movie Interstellar. You maybe also saw this scientific paper which was based on the calculations performed for this movie, and these calculations were performed very well, but they actually assume that the black hole itself is surrounded only by vacuum, and the light is coming or the source of this light is actually not specified. They are just looking at the light trajectories around compact object, around the Kerr black hole basically, and all of this is basically I'm not saying it's wrong or it's something bad, but I like to say that actually we can do better. And what you can do better, what is actually usually used is geometrical optics approximation, where you basically assume that the wavelength of the light trajectories which you analyze are much shorter than the scales over which the properties of the medium vary, and also the curvature radius is much larger than this characteristic scale. And also you have to assume that this wave is monochromatic. So again, the wave properties don't vary at the scales which are comparable to the wavelength. And if you do have such approximation, and if you assume that this kind of things, then you can basically speak instead of trajectories in terms of rays, which is very useful, and you can then perform the analysis of this situation much more easily, because you are and you can think about these trajectories as rays, which is very useful. Moreover, or not moreover, what should be stressed is that this approximation is typically assumed for non-dispersive isotropic medium. But if you also justify that you can use such approximation also in the dispersive and anisotropic media, then you can apply this approximation as well, but you have to be careful that there could be some limitation. But what is typically done in this formalism which I am working with, I actually assume that I can perform geometrical optics approximation for dispersive media, and it seems that for the media which are in the game, it is good approximation. Well, when I assume that I have the geometrical optics, and I would like to investigate the light rays around compact sources surrounded by some medium, I can apply the Hamiltonian in this form, which was originally obtained by Singh in his book in 1960. And this Hamiltonian basically merges together space-time metric, which characterizes the compact object. It characterizes the medium, which is here defined in terms of its refractive index and velocity, and also momenta, which are the wave momenta. So it characterizes the wave itself. And when I assume, or not, I don't assume it is the definition of this scalar product of the wave momenta and the medium velocity. It is the wave frequency. And the Hamiltonian formalism, or the Hamiltonian approach, is very convenient, especially because I can then obtain equations of motion from the Hamiltonian. So it is quite straightforward to get them for different setting, for different choices of spacetime, and also the momenta and the medium, of course. Then I can write down the equations of motion, and they are very useful in terms of defining deflection angle, as I will show you later. But I am now, so what I want to do is that I want to find or write down the Hamiltonian, and then from them I can define the properties for the light propagation. I mentioned medium several times. Usually this medium is supposed to be dispersive and refractive, just to be sure what I mean.
Question?
Yes.
Is it easy to see that the previous Hamiltonian in the once taking the flat space limit reproduces the familiar geometric optics? I'm trying to do it in my head.
Sorry, what do you mean by geometric? Oh, do you mean whether it is whether I can apply it in terms of geometrical optics, or?
So I want to see that if I take G to be simply eta, the flat space
Minkowski
metric,
Mhm.
then I would like to confirm and know velocity, or time-like velocity. Then I would like to reproduce the, I don't know, the Fermat's principle, or whatever is the correct way to think of ordinary ray optics in uncurved space time.
Well, it is actually the best way, or not the best, but as I usually look at it, is that when I set that a refractive index equal 1, then this term disappears. And I'm left up only with this Hamiltonian, which is precisely the Hamiltonian known from GR for vacuum. So then everything holds. And of course,
That's true.
and
But
of
it
course,
is not the limit that I was looking for, yes.
yes, that's one thing. And then you have to verify, or actually it's in terms of refractive index. So basically for given medium, you have to look whether you can apply that. And of course it depends on the space-time metric definition, but for usual things which under which it is suitable to reproduce all these things, it is useful to assume that the metric will be asymptotically flat, which basically also leads to Minkowski for a large R. Yes. So then you can reproduce, and you can safely do that and reproduce that. So yes, this Hamiltonian is fine, but I should maybe stress
No,
that.
but suppose that you have a light ray in flat space moving in a medium where n is space dependent, where the index is space dependent. What Hamiltonian would we use in flat space?
Yes, and I cannot see why shouldn't I use this Hamiltonian. The only thing here which I should maybe stress is that when I have these Hamiltonian equations of motion, then when we are in vacuum, then this lambda is affine parameter, which is not case for the dispersive medium, for general medium. That it is not. It is here. It is not affine parameter, but it is not significant problem for this formalism. So in
Okay, thanks for now.
Okay. So, yes. So I just want to stress that the medium is dispersive and refractive. What I mean by that is that the refractive index is not equal to 1, and dispersive that it also depends on the wave frequency, just to clarify that. Usually what is performed within this formalism, it is called plasma approximation, which I will discuss briefly later, which is very specific in some sense, but it can be performed, discussion also for general medium, which was performed in this work, but it was performed for only spherically symmetric spacetime, for general spherically symmetric spacetime. And as I said, cold plasma approximation is usually used. It is specific because, okay, I should maybe say that a cold plasma approximation means that the phase velocity of the in this medium is much larger than the thermal velocity of the species forming the plasma. And the refractive index for the cold plasma approximation look like that, where this omega PL is the plasma frequency for electron, which depends on the density of the medium. And if you plug this refractive index into the Hamiltonian, which we discussed before, then you obtain just very simple form where does not depend on the velocity of the medium at all. So it means that for the rays, it actually doesn't matter whether the cold plasma moves or not. The ray trajectories will look all the time the same. And also there is one thing that in order to propagate the wave in plasma should have the frequency of the wave should be larger than the plasma frequency. And but yes, this is one thing just for general waves in cold plasma approximation. But again, here it is a very specific term, and also it can be also viewed that it effectively corresponds to the to moving of the massive particle with effective mass equal to plasma frequency, and it actually moves in vacuum. So it can be viewed in such, and then it actually corresponds to everything which is known from vacuum case, which is very convenient because then you have something which you can compare to and also look and it's something from different way, and what is true in this approximation should be also true in the other. Yes, this is something which I already said, that there is this formal correspondence between the massive particle and vacuum here, and also between this Hamiltonian, which is a nice coincidence.
But Barbora, can you repeat? Maybe I missed how VTH is defined in the one
Sorry?
slide. VTH in the upper part of the slide.
VTH.
Yeah.
It is thermal
How-
velocity. It is thermal velocity of the medium sorry. Yes, of the particles forming the medium. So you would have to take.
I see, like a characteristic thermal velocity.
Yes. Yes.
Okay.
Yes.
Okay.
And so this is called plasma approximation, and I would like to stress that in most of the previous works, only cold plasma was considered, and also that the medium velocity was not discussed at all usually, or static medium was assumed at least, because you don't have to need to take care too much about the velocity, because in cold plasma the velocity drops out from the Hamiltonian. And as I said, what can be first thing which can maybe be studied in this is when I assume that I have some single light ray which propagates around the compact object, then this light ray would be normal, or even in vacuum somehow bent. And how to characterize bending of such a light ray is its deflection angle. The deflection angle is characterized in the equatorial plane, and it is basically the deviation from the straight line, how which would be the light trajectory for vacuum around compact object. So I would have just the straight line, and then the deviation from this straight line is the deflection angle, which is caused by the presence of the object, and as we will see, also by the medium. What is interesting is that you have to integrate over this f. Curl f, which is basically ratio of the two equations of motion, and that's why I also need to define the equations of motion in order to characterize the deflection angle. I would also like to stress that this deflection angle is typically defined in the equatorial plane or in some plane, and if you would like to define the deflection angle outside this plane, then it would be complicated, and this idea actually doesn't work. So everything which when I will be speaking in terms or about deflection angle, it will be only in the equatorial plane, which is fine for spherically symmetric case, where this plane is not somehow special because of the symmetry of the problem. Then you can choose some plane according to your will, and it will be no loss of generality. It is slightly more complicated for the axially symmetric space-time, but if you are able to say that you don't mind, or if you just can survive that, then it is actually no problem. But it's at the moment the best way how to do that. And I several times.
Barbora, can I ask another question?
Mhm.
So, sorry, going back to the cold plasma one slide
Okay.
ago.
Okay.
So just to get an astrophysical idea, so M87, Sagittarius A star, for example, in the EHT frequencies, are they in this approximation, or
So
do you have an
going
idea like off the top of your head, or I mean, no, maybe.
So going back to the M87, when I would like to speak about plasma in this sense, in this case, the thing which is not at all mentioned here, and it is actually not, and I won't mention at all, is that it is this, all the setting here is for non-magnetized plasma. So first thing which is problematic here is that you have to involve magnetic field into the description. So
I see.
that's actually, and I also suggested it as my postdoc project, that adding into this formalism magnetic field would be very beneficial in terms of real astrophysical applications. If you would be interested in some numbers, so then it is from the form of the refractive index, as you can see, is that you can see that that the effect of medium would be very close to the plasma frequency, which is where this ratio is actually largest, because when you have larger waves, then the waves will be this number will be very small, and the refractive index will be basically close to 1. For the numbers which are known from M87, the plasma frequency is something about hundreds of megahertz, and the observations for M87s are something like 100
Gigahertz.
gigahertz.
Yeah.
Yes.
Yeah.
So at the moment, it is not observable, these effects.
Okay, thanks.
So this is what I wanted to say about the deflection angle, and as I mentioned several times, it is that now you have to also define, in order to calculate the deflection angle or something, or at least anything, you have to define both metric and also the medium. So for the metric, let us now choose the general spherically symmetric static object, which can be in general defined by these three functions, which are due to the symmetry only functions of radial coordinates, and we assume that this metric will be asymptotically flat. So we assume that these functions are positive and behave at an infinitive like that. Due to the symmetry, it is also convenient to assume the same symmetry for the medium, so we also assume that the medium is spherically symmetric. It is just my choice, because then I can calculate it easily, so it is that I said, okay, I will assume that the medium is spherically symmetric. I will actually assume two kinds of media. The first would be radially falling medium, which I define like that I assume that it has only, besides its time component, it will also have a non-zero radial component, where I assume that it will be, due to the symmetry, also just function of r. And from the normalization conditions on velocity, I will assume this, I can calculate this form of V naught, which I know, but in the final results, I will just keep V naught, and I know that I can then plug everywhere this form, but just because of the compactness, I won't do that. And here I also assumed that P naught, it's because it's actually constant of motion, and I can define it like the the wave frequency at infinity, and for some cosmetic details I will call it omega naught to be equal minus P naught, just because it's convenient to do that like that, but just the small change. And I can, for such defined medium, I can define the photon frequency, which now reads this form where everything is known, and I can plug for V naught. And I would like to see how this change of the photon frequency, or the individual terms of the velocity, enter the individual terms, and also, for instance, change the deflection angle, which would be useful. But as I told you before, the cold plasma is not suitable approximation for that, because in cold plasma, the Hamiltonian does not depend on velocity. So I have to do, besides defining the medium velocity, I also have to define somehow its refractive index. If I don't do that, which is shown here for the equatorial plane, I can also only here write refractive index in its complete general form. I can write the equations of motion in the general form, where I just know that there will be some partial derivatives of these terms where the medium manifests. But this is everything which I can do, and I cannot do very much, and it is not very instructive, and I cannot really say a lot about such forms. So for this reason, I will I will introduce new refractive index, which is very general, which is just a function of the omega of the wave frequency, which I know, and some functions A0, A1, and A2, which I have to just I want to know to say that refractive index has to be the square root, or sorry, the refractive index squared has to be non-negative, and the group velocity has to be lower or equal than the speed velocity. And if I assume all these things, I can then plug this form for the refractive index into the Hamiltonian. And here I can see that I obtained something where omega, because we know the omega is function of the velocity, of the medium velocity. And this is something which I can already calculate. So I can now work with this Hamiltonian and calculate the deflection angle. And it is actually, it turns out that this refractive index, when I plug for omega and do some manipulations, I can rewrite the Hamiltonian as a quadratic in terms of the PR, which is the radial component of the wave momenta. And it is useful for calculations of the equations of motion, and also for compact notation of the final result, as you will see, where I can introduce all these three functions which are defined here, and it is just to see how that I know what they are. I can calculate them, but I will then use in the final forms these three functions, because it's just more suitable, and also it's easier to calculate with. As you maybe remember, the deflection angle depends only on dr over d phi, or opposite, and I am also interested, besides this dependence on PR, on function of p phi, which is the equation of the constant of motion for this system as well, and it enters only at this one position which is present here, so I can also write it here. So it is then very convenient and straightforward to calculate the deflection, the equations of motion. When I do that, I can then write the form which of the d phi over dr, which looks like that, where you can see that these functions are actually known from previous slide. This is the metric function c, and this is the constant of motion p phi. If I introduce this function h squared, which is useful because then I can get rid of this ratio of the constants of motion, which I can basically then identify with this function h squared as a function of capital R, which is the closest radial distance, which also was shown in the plot with the deflection angle. And if I do this and then plug into and calculate the deflection angle, I will obtain which would look like that, which is quite nice, because it is you can see that it is just very brief function, but it's just the form of notation. What is nice here is that when I compared this result with previous literature and also with the vacuum case, I am able, from the definition of the A, B, and C curl, I am able to trace the particular effects of the medium velocity, which enters now here, and I'm also able to trace the dependencies of the constant of motion, because I know that h squared capital R is actually the ratio of the constants of motion. This was for how much time do I have? Yes. So I can now use this result for particular examples, because I here had this general form of the refractive index. It does not correspond to any specific case, medium, so I can now look how this form of the refractive index will change for particular examples. And if you think about that, then basically what changes is that the definitions of A, B, and C and H change. So here I will just show the results for basically how the diffraction angle look like. The first thing would be cold plasma. As I told you, cold plasma is actually specific because it does not depend on the velocity at all, but it was found in the literature previously, so it is good to compare new results with the previous results, and here it is just to see that everything works, and so everybody is happy. So it's one thing. The second thing would be non-dispersive medium. Non-dispersive medium meaning that the refractive index does not depend on the frequency at all. So I know that the only thing how the frequency enters is the velocity terms, and I know that n is not function of the frequency at all. I can also obtain something useful in terms of ABC and then H, and if I plug them into the formula for the deflection angle, I can calculate them, which is fine. And the last thing would be something like a toy model or some non-specified medium, just to see how the effect of the velocity would manifest, where also the omega is present when the when the medium is dispersive. And if I do that, I can then also calculate again A, B, and C functions and H squared, and I can plug them. So I can and here in these functions I can directly see where the effect of medium enters, because I know that f is function of it is component of VR. So here I can directly see which terms enter here due to the non-static case of the medium. Second case, which I would like to briefly discuss for the spherically symmetric object, would be rotating medium, where now the radial component of the medium is 0, but instead v phi component is non-zero. Again, I can find V0 function, which is known, but I will use just V0 because of the compactness. And here the function, the wave frequency is not PR, function of PR anymore, but is function of P phi, just due to the definition of the velocity. So the frequency changes. And what is interesting now is that when I assume again this general form of the refractive index, where now the wave frequency is function of this p phi because it's defined like that in comparison to the radially falling medium, I actually find out that now the Hamiltonian is quadratic in p phi instead of pr, and again pr enters just at this last in this last term. These functions a, b, and c phi curl are actually different than in this previous case for the radially falling medium, but they can be found, and I in my paper they are shown, but I don't think it's very much useful. And at this stage, the only thing again is that as it's actually similar structure as to previous case, that this PR again enters just at this one place, so it is very easy to calculate the equation of motion for R, because it's just this partial derivative of this term. So it's very easy. And if I actually do the similar calculations as I did in the previous case, when I apply the functions on the definition of the deflection angle and perform some manipulations, I can actually end up with something which look like that. Here you can see that B is again metric function, so it enters from the static object. These A curl and B and C here are again functions which are known and can be easily wrote down. And H is now new function which looks like that, but it has the basically similar meaning. What is now interesting here is that actually here enters the plus minus sign. So it tells me that it depends on for the light trajectory whether it moves in the same sense as the medium moves or in the opposite sense, and then the deflection angle changes. And this is what this plus minus sign tells me. And please take just this object, like the structure of this object, keep it in mind, because I will back to that later. Because what I want to now see is to take axially symmetric stationary spacetime, which would be defined with the metric which I say, okay, the metric will look like that. I will assume this function. Now the situation is slightly more complicated, because for the axially symmetric spacetime there is also additional dependence on theta, and if I am in the equatorial plane, I can do that. I can say that theta will be equal to pi over 2, which is not good, but it's actually some loss of generality, but I cannot do better for the deflection angle. And the Hamiltonian will now look like that, where there will be again the function of the medium hidden in this W function. And if I assume that the medium will be now static, so it means that it will have only one non-zero component, which will be the time component. And I will assume that the refractive index, the W function will look like that. I can obtain the deflection angle formula which looks like that. You can see maybe that here this term, maybe I can go back, is formally the same like for the spherically symmetric object for the rotating medium. And here we have actually rotating object and static medium, which, yes, we can discuss how much realistic this assumption would be. But it is nice to see that actually for the deflection angle, it actually doesn't matter whether the medium moves or whether the object moves. Again, the situation is the same. It will be difference between the medium or between the light rays, whether it moves in the same sense as the object moves or in the opposite sense, and we can see that the difference here enters in terms of this change of sign. I would like to stress that here this function h was actually defined for completely general medium given by just its refractive index. So basically any medium can be entered here, which is good and it is more general. But it is fine to for instance plug the cold plasma case and it can be reproduced from the known results, which I will discuss briefly, which I will discuss actually right now, is because what I wanted to do when I obtained this formula is that I would like to compare my results with the results in the literature previously done, and of course Scatter was done very soon. In the equatorial plane, the functions a, b, c, and p entered in the metric function in the metric. They look like that. If I plug them into the deflection angle formula, which is here, and I will assume that the medium is called plasma, then I am able to reproduce the results which were obtained by different method in this monograph. So everything works, it is fine. And I would also like maybe to slightly touch this dependence of these two signs, which is here.
So, Barbora, can I ask a question? So just if you go back to this expression, yeah, so for the deflection angle, so if I think about like the leading effect of the plasma compared to just you know I mean, yeah, like the leading effect of the plasma basically compared to just vacuum. So what would it be?
It
How would it
depends.
affect?
It depends on how you define basically this omega plasma, this plasma frequency, because it's function of the density, and then it depends how you define the profile of the density.
I
So
see.
it is what is usually done is the power, you assume power law density, then you have to so it will be additional term which will decrease as 1 over r to some k, which I will show in a minute.
Right.
But it will depend on this concrete choice.
I see. Okay. So it's not that it always goes in a certain direction. It depends on how you define this
Yes,
function.
you have to define the density profile and then you can calculate plasma frequency from that. And
I see. And another question. So the reason why you focused on the equatorial plane for this axisymmetric case
this is what I said, that actually definition of the deflection angle outside equatorial plane is complicated.
Right. Even in Kerr or
In
I
general.
mean in general.
It is actually not related to Kerr. It is actually related to how you define because the most intuitive case how to define reflection angle is that you have just the plane that your light ray moves in a plane and somehow bends.
Right. Okay. Yeah. I
And
guess I understand that you need a more elaborate definition because it's not just
yes,
one angle of
yes,
deflection.
yes, that's what is usually done in the literature, that they assume actually two angles, but
You need
then
some
you,
Euler angles or something like that,
yes,
no?
yes, you have to do something like that. Yes. And in this case, maybe it's just better to integrate over the geodesics and then calculate. And the question is how to do it analytically. You can do it definitely numerically, but I don't know how
But
to
you're
do
not
it.
guaranteed to be able to do it analytically every time, right? Because you don't have the Carter constant. And, if
In
it's
the
a
equatorial
general
plane, you do in the equatorial plane,
the
you
equatorial
don't
plane
need
you
a
do.
Carter constant.
Right. Right. But okay, that was what I was trying to ask, whether that's why you focused on the equatorial plane.
Yes,
Because you don't.
you
Right.
basically can assume any other plane, right? Because when you fix your theta, then you are able to calculate. You should be able, but the equatorial plane is most intuitive way how to do that.
Okay, thanks.
So I wanted to show that it matters how the light rays propagate with respect to the rotation of the object. This is just for simplicity done for vacuum, just to show when we have the same direction of the light propagation with respect to the rotation of the Kerr black hole, and whether it is opposite. So you can see that due to the definitions of the radius horizon, horizon radius, which is this horizon is the radius of this circle is given by the horizon radius, and this is the radius of the photon sphere radius. So due to this, and you can also here now nicely see that here for the counter-rotating case, the much more larger impact parameters of the rays are actually affected by this presence of this object, and you can see that they are dragged by this object. So it is just to demonstrate that for these reasons, which are now here, I think very obvious, is that I will only focus on the co-rotating case for the metric. So just to see that it is what one would expect. Another case, what would be nice to study, and actually Professor Bichak wanted me to study, was Hartle-Thorne metric, which is usually used for the neutron star description. And it is much, you can see from this already from here, that it is much more complicated than the Kerr metric. What is here the most substantial thing is that here enters this new parameter Q, which corresponds to the quadruple moment. And this characterizes it is new parameter which enters the metric. And the question actually which Professor Bichak wanted me to answer was how the presence of this quadruple moment changes the light trajectories and light bending.
So, Barbara, sorry, can you go back? So these angle brackets here?
Sorry?
These
Yes,
angled
these are
brackets.
just additional brackets. It is not
Oh,
averaging or something like that. It is
okay.
just because there are so many brackets and you are running out of what you can apply. So it is just no specific meaning.
Okay, and correct, just to understand, correct me if I'm wrong, if I take the Kerr geometry, so that will imply some specific values for all
I
these
will I
parameters.
will I will show
Okay.
you right now, basically, or
Okay, good.
after a minute.
Okay.
So here is just to understand more this structure. M is total mass of the object, J is total angular momentum, and Q is quadruple moment, as I said. These functions which enter here, P2 and Q2 and Q1 and so on, they are Legendre are the functions or polynomial of the second order. And here I will just introduce this notation just to make this ugly formula more compact. And now when I want to go back to Kerr, which I know, Actually, what I know or what is done for Kerr is that for Kerr metric, this parameter Q equals 0. And that's because for the Kerr metric, the quadrupole moment equals this very specific form, this total angular momentum square over its mass. So K equals 0. And then for Kerr, J equals minus MA. If I do this thing, and then because this Hamiltonian metric was not defined in the biolinguist coordinates, I have to perform this coordination transformation of the coordinate. If I do that, I'm able to reproduce the Kerr metric. So I hope that answers your question.
Yes,
Okay,
thanks.
good.
Yeah.
Because it's not. But what is good? I have this formula for the deflection angle. I can find my A, B, C, and P parameters, and I can calculate basically the deflection angle for them just to define from the definition of them. Here I actually didn't consider the whole approximation because there will be more terms. I just assumed the first order or jump up to some order, but I was able to find out analytically this form for the deflection angle. And to compare the deflection or the light trajectories around Kerr and Hamiltonian metrics, here you can see that for the light rays, for the dash dotted lines, curves correspond to the vacuum case, and these solid lines, orange and yellow, correspond to the two examples of the cold plasma, where I assume that the plasma frequency will equal this form, where you can see that it is the power law definition, where I have two functions of K, two choices of K, one equals to pi 5 halves and the second corresponds to 7 halves. And here you can see actually the most, for me at least, the most interesting thing is because when I have a medium which surrounds the object, I would assume naively that the presence of the medium will cause that the light rays will be bent more. But here you can basically see the opposite, that due to the presence of the medium, the light rays are bent less than in vacuum, because here the vacuum is the dash dotted case. And the reason for that is that in plasma, the refractive index is always lower than 1. And this is just the nice manifestation of this property. And because still Professor Bichak was not happy with my answers how the presence of the quadrupole moment changes the light trajectories, because here I just had to make choice for one particular choice for Q. Here it was equal something like 2.5. Something which I did now was that I took more choices of Q, of the quadrupole moment for the Hamiltonian metric. And I calculated the deflection angles and also the light trajectories for various choices of Qs, where this dash dotted case now corresponds to the Kerr case. And from here, I think here it's more obvious, you can see that actually it is not any specific case in sense it will be limiting value, everything will be larger or lower than the Kerr case. No, it's just some specific choice of the quadrupole moment which I did, and I was able to calculate that. So actually the presence of the quadrupole moment in the Hamiltonian metric can lead to both cases. Either the deflection is lower or larger. It depends on the particular choice of the quadrupole moment with respect to the Kerr metric. And so this is something which I wanted to show explicitly. And just one small comment which I wanted to do was that I also mentioned this ratio of the P phi over omega naught. This ratio actually corresponds, at least in this formalism and at least these choices for for metric the impact parameter, which is defined like this ratio is impact parameter corresponds to parameter. And what is usually done that it is good because this parameter is coordinate independent, and it is usually the deflection angle, at least when it's done or it can be done both cases, but when it's done like a series and in some leading terms, it's usually expressed in terms of this impact parameter because it is very convenient to do them. But if you want to do that, you have to find the relationship between the impact parameter and between the minimal radial distance capital R. And from my calculations, which were published in my work with Professor Bichak, I was able to find this general form for the relationship between the capital R and impact parameter. For instance, for the Hamiltonian metric, when I assumed vacuum and k equals 0, so basically Kerr metric without this coordinate transformation, I was able to find this direct relationship between and calculate direct relationship between impact parameter and R. But here it was actually done more general, and for arbitrary metric I can from this obtain the relationship, which is quite useful. And it is useful because also many literature performed the calculations of the deflection angle in terms of impact parameters. So one it is very typically what can be done when one wants to compare the two or the known results from previous studies. It is usually useful to express the result in terms of the impact parameter. Okay, so I think that it's the time is fine, so I can conclude that I wanted to present you the general approach how to analytically study the light rays around compact sources surrounding my medium, which is usually dispersive and refractive. I showed you two examples for spherically symmetric space-time. One was radially falling, the other was rotating. I compared the results for the static medium around axially symmetric object, and I showed you also the ray trajectories for Kerr metric and Hamiltonian metric. I also introduced this Hamiltonian metric, and I also, due to that, was able to discuss the presence of the presence of the quadrupole moment actually can change the light trajectories both ways. Either it is the light rays are deflected more or less. It depends on the exact choice of the quadrupole moment. And I also briefly discussed the relationship between the impact parameter and the closest radial distance, capital R. And if you are interested in more of this, you can check the literature. So thank you for your attention.
Thank you, Barbora. All right, any questions? So I actually have a question. So, you know, there is a relation between light trajectories and quasi-normal modes in the iconal limit, in the very high frequency limit. Right? So quasi-normal modes, these solutions of the wave equation, basically, around black holes that are important in gravitational waves, etc. But there's a correspondence in the iconal limit between these and the photon orbits, kind of like it always works. When you take a wave at very high frequency, it becomes like a particle. It moves on a geodesic. And so I'm wondering whether anyone has considered quasi-normal modes in the presence of a plasma, for example, because one can imagine that could also affect the quasi-normal spectrum of a black hole if you have some medium around it. Are you aware of anything?
I am not aware of anything like that.
Okay.
I would be interested in the typical frequencies of these modes. Do you know?
Well, the frequencies of the lowest line modes, the most important ones, go like are like the black hole. You know, they go like 1/m for non-rotating, right? least for a non-extremal black hole. So
Mhm.
they have the characteristic frequency of the black hole. And if you take this to the Eikonal limit, then you have actually a tower of such modes, which goes to higher and higher frequencies. But the most important ones are around the characteristic frequency of the black hole.
Mhm.
And that's why I'm also asking, because these are actually, they have lower frequency. So I think they have more chance to be right. I mean, it's more likely that they will be affected actually by this kind of effects.
Yes, and
Uh,
there would be also the question, how is their frequency with respect to plasma frequency, whether they can still propagate in plasma or not.
yeah. Well, of course, I mean, for gravitational waves, they're much less affected by matter surrounding the black holes. I'm guessing, but let's say electromagnetic quasi-normal modes, you have them also for electromagnetic fields. Then I guess these could be more affected. Yeah, I'm just wondering because I mean, that's also something that should be, it's also being, people trying to observe. So
Mhm. No, I'm not aware of that, but maybe somebody did not within this formalism, but independently. I would have to check. I'm not sure.
yeah,
Not aware of this in terms of this formalism.
mhm. I mean, it could be even that just using a refraction coefficient won't be enough. I don't know, won't be general enough, because it's already like waves and not light rays. At least in the Eikonal limit, one can imagine that it would have a similar effect.
Yes, that would then mean that you have to compare the wave frequency. That's why I'm asking about the frequencies, right? Whether it is still
Yeah,
possible to do this formalism, or you have to just do the complete description, not complete, but different description.
yeah. All right. Any more questions? Okay, if not, let's thank Barbora again. Close the recording.